Good morning, good afternoon, or good evening. I hope you're having a wonderful day today, and welcome back to Unit 5, Circular Motion. Before spring break, I posted some videos where we reviewed lessons 5.1 and 5.2. And if you haven't watched those videos, this would be a good time to go back and review the concepts in those two lessons, because we're going to be using the concepts from these lessons heavily in today's lesson, which is lesson 5.3, Equilibrium. So let's start with the concept of center of mass. If you imagine throwing an object through the air, the object, may tend to spin as it flies. And if we were to trace the path of some random point on the object's mass, that path could trace out a pretty strange shape. Like, for example, imagine this wrench flying through the air. If we were to trace the path of this little hole in the end, it is quite a strange path indeed, and not at all reminiscent of a parabola. But there is a point inside the wrench's mass that will always travel in a parabolic pathway as it flies through the air, and that point is the center of mass. So as the wrench flies through the air spinning, each point on the wrench will trace out a different weird shape, but the center of mass will always follow a nice, smooth, parabolic trajectory. To find the center of mass of an object, imagine suspending that object from a string. The object will always hang so that the center of mass is directly beneath the string that supports it. So if we trace an imaginary line going straight down from where the string connects to the edge of the object, that line will always pass through the center of mass. And if we suspend the object from several different points, we can trace those lines and they will all converge on the center of mass. So in this case, we have a tennis racket tied by a string. We extend that imaginary line downwards, it passes directly through the tennis racket's center of mass. And then if we tie the tennis racket at a different point, the tennis racket will always spin so that the center of mass is directly beneath the string. Center of mass can give you some idea about how stable an object is. Here we have the same object, but on the left it is sitting on its wide base, and on the right it is sitting on its narrow base. The center of mass is quite close to the wide base, so when the object is sitting like this, it is more stable than when it is sitting like this. If you can imagine, if a cat were to walk past these two, the cat would definitely be more inclined to brush against this one, because cats just love to knock stuff over, and it would be much easier to knock over this shape than it would be to knock over this shape. If this shape starts to tilt, it will become unstable and tip over on its side as soon as the center of mass passes its support point. So that's what we're going to do. We're going to run a little animation where both shapes are tipped, and we want to see how far they have to tip before they will start to tip over on their own. Let's start with the shape on the left, which we said was the more stable shape. As it tips, the inclinometer will measure the angle at which it is tipped. And then once it tips past its support point, it becomes unstable. This shape has to tip by 66 degrees before it becomes unstable, and now it will continue to fall the rest of the way over onto its side. If you stop pushing before you reach 66 degrees, then the shape will just fall back onto its wide base. Now let's look at the shape on the right, which is the same shape but upside down. And we start to apply a force to tip it, and it only has to tip about 12 degrees before it becomes unstable and will continue to tip over the rest of the way. Theoretically, if you could get the shape so that the center of mass were perfectly balanced above that contact point, it would balance there, but that's very difficult to do because that point is very, very small. If you've ever tried to balance a chair on two legs or even on one leg, you know it's very difficult, and the slightest force will cause it to tip in one direction or the other. Here's another example. You have a crate that's sitting on its base, and someone is applying a force to the upward corner of this crate, which, because the force does not pass through the crate's center of mass, it exerts a torque, which causes the crate to start to rotate. Now, while the center of mass is still over this base, the weight of the crate will apply a counter torque, which would cause the crate to want to rotate back down onto the base it was sitting on. And if you stop applying the force at this point, that's exactly what the crate will do. When the crate reaches this point where the center of mass is directly above the contact point, it is theoretically balanced. Again, it would be very difficult to get the center of mass to be exactly lined up with that contact point because the contact point is so small. If you continue to apply force to tip the crate over, then eventually the crate's center of mass will no longer be over its original base, and now this weight will provide a torque that is in the same direction as the torque you're applying by pushing the crate. So the crate now, if you let go, will continue to tip and will land on its side. But there's nothing breakable inside that crate. Let's talk about the concept of static equilibrium. When the net force acting on an object is zero, then we know the object will not accelerate. This goes back to Newton's laws of motion. Well, when the net torque on an object is zero, then there will be no changes in the object's rotation. In other words, it will have no angular acceleration. And when both the net force and the net torque acting on an object are zero, then we say that object is in a state of static equilibrium. It will not experience a change in either its linear velocity or its angular velocity. So here's a skill practice problem. Let's see if we can solve this problem. Copy it and paste it onto another page so I have a little bit more room to work. Follow along with me. Make sure you understand the steps of solving this problem. It says a woman with a mass of 65.0 kilograms is doing push-ups. What are the vertical forces acting on her hands and feet? So the first thing we want to do is to draw a force diagram. Just establish what forces are present. The first force that you're working against when you're doing push-ups is your weight. And weight always acts through the center of mass. So we can draw an arrow coming straight down from the woman's center of mass, and we will label that arrow FW to represent her weight. Now there are also two forces that she is exerting. One force exerting upward arms. We will call that FA, the armed force, not the Marines or Army or Air Force, the armed forces, this being the force that her arms are exerting. And there's another force being exerted vertically through the feet, and we will call that FF, for foot force. Now let's write a net force equation. The net force acting on this woman's body is equal to the force exerted on her arms plus the force exerted feet minus the force exerted by her weight. We can assume that the net force will be zero because the woman is neither accelerating upward or downward. To be fair, there is vertical acceleration. When she reaches the bottom of each push-up, then she'll accelerate upwards, and when she reaches the top of each push-up, then she'll accelerate downwards. But in the middle part, when she's either moving downward or upward at a constant speed or constant velocity, the net force should be equal to zero. So we will go ahead and say that 0 newtons is equal to FA plus FF minus FW. And now we can add FW to both sides. Since this side is 0, we can say that FW is equal to FA plus FF. And this makes sense. The amount of force exerted by her hands and feet should add up together to equal her weight. She's supporting her entire weight on her hands and feet. We can further say that since her weight is equal to mass times gravity, mg is equal to Fa plus Ff. We'll come back to this formula in just a few moments. But first, let's talk about the torque that the woman's body is exerting. First of all, there's the force of weight, which is pulling downward. If we imagine that when you're doing push-ups, you are pivoting around your feet. So this weight force is exerting a torque this direction. I'll represent that using a curved arrow. We will call that tau W, the torque exerted by the woman's weight. It wants to rotate her body in this direction. Now, because that direction is anti-clockwise, we will call tau W positive. Also, her arms are exerting a force that want to force her body to rotate in the opposite direction. So we will call that tau A, and that is going to be negative. Tau A is clockwise. That's the same direction that the hands of a clock move. So just as we wrote a net force equation, we can also write a net torque equation. We can say that tau net is equal to tau W minus tau A. And again, tau A must be negative because it represents clockwise rotation. That's just the convention. It actually doesn't matter whether you make tau A negative or positive as long as tau W has the opposite sign. You're still going to wind up getting the same answer. But just by convention, call clockwise rotation negative. Now, when the woman is in the middle of a push-up, then the net torque acting on her body should be 0 Newton meters because her rate of angular velocity is not changing. So 0 Newton meters is equal to tau W minus tau A. And add tau A to both sides and say tau A is equal to tau W. Remember from our previous lesson that tau, torque, is equal to force times radius times sine theta, where theta is the angle between the line of force and the radius of rotation. In this case, the line of force is perpendicular to the radius of rotation for all of these forces. So in all three cases, theta is equal to 90 degrees and sine theta is equal to 1. So we can leave that out. We can leave sine theta out. It's not really necessary in this case. We can simplify a bit. All right, so we'll say that for tau A, that works out to be force A, which is one of the things we're trying to find, multiplied by radius A, where radius A is the distance from the axis of rotation to force A. It's going to wind up being 1.00 meters plus 0.50 meters, and we'll get that in just a moment when we start substituting. Tau W is going to be equal to force W times radius W. Okay, remember, her weight, Fw, is equal to mass times gravity. So we can say that FA-RA is equal to mass times gravity times Rw. And now we know all of these values except for Fa. So we can substitute in the information that we know and solve for Fa. I'll come up here with this. Fa times Ra, which is 1.00 meters plus 0.50 meters, for a total of 1.50 meters, is equal to her mass, which from the problem is 65.0 kilograms, multiplied by gravity. We assume this woman is doing push-ups on Earth. She's probably not on the moon or on Mars doing push-ups. So G is going to be equal to 9.81 meters per second squared. And then Rw is the distance from the axis of rotation to her center of mass, which is 1.00 meters. So grab your trusty calculator and let's punch these numbers in. Fa times 1.50 meters is equal to 65.0 times 9.8 times 00, which, when you round it to three significant figures, is 638 Newton meters. Kilogram times a meter per second squared is a Newton. And then we have one more meters to multiply in there, so that's Newton meters. And of course, that's what we would expect because we're solving for torque, and torque is measured in Newton meters. Now to solve for Fa, we divide both sides by 1.50. 638 Newton meters divided by 1.0 meters gives us 425 newtons. So that's the first part of our answer. Woman's arms are exerting a force of 425 newtons while she's doing push-ups. Now we can come back to this equation we established a moment ago. We know the value of Fa, know her mass and gravity, so we know everything but Ff. Now we can solve for that. So her mass is still 65.0 kilograms. Gravity is 9.81 meters per second squared. Fa, we now know, is 425 newtons, and Ff That's what we're trying to find. 65 times 9.81 is 638 newtons. It's the same thing it was up here because we just multiplied by 1. So that's 638 kilograms times meters per second squared, which is newtons. That's equal to 425 newtons plus FF. If we subtract 425 newtons on both sides, we're going to find out that FF is equal to 213. So the force exerted by the woman's feet is 213 newtons, and the force exerted by her arms is 425 newtons. And if we add those two forces together, we get 638 newtons, which is the woman's weight, so everything checks out. For our next problem, this is very similar to the one we just did. It looks very different, but our technique for solving it is going to be similar. So we'll copy that problem, paste it onto a new page to give myself a little bit more. A 5.8 kilogram ladder, 1.80 meters long, rests on two sawhorses, which are labeled A and B. Sawhorse A is 0.60 meters from one end of the ladder, and sawhorse B is 0.1 meters from the other end of the ladder. What force does each sawhorse exert on the ladder? I know this looks like a very different problem from the previous one, but it's actually quite similar, and we're going to be using the same technique to solve it. So let's start by writing a net force equation, let's start by drawing a force diagram, and then we will write a net force equation. So first, we'll draw the arrow representing the ladder's weight, which always passes through the ladder's center of mass and is straight down. Call that FW. FW, as we know, is equal to mass times gravity. Get back to that in a moment. Now there are two forces exerted by the sawhorse force, and they are straight up, so we will call that FA because it's exerted by sawhorse A, and we have to call it something. Call this FB because it is exerted by sawhorse B. Now we can write our net force equation. So we will say net force is equal to FA plus FB minus FW. And we're treating the weight as negative because it is in the downward direction, whereas FA and FB are both in the upward direction. This ladder is neither accelerating downward nor upward, so the net force must be equal to 0 newtons, which means that we will be able to add the weight to both sides, which will give us weight is equal to FA plus FB. Okay, which is something you could probably have already guessed, just showing you the logical steps that get us to this point. The weight, of course, is equal to mass times gravity, so we'll say mg is equal to FA plus FB. And we will come back to this equation in just a moment when we have some more information to plug into it. Now, let's define the torques that are acting on this ladder. First, we need to define a point of rotation. And I would choose the top of either sawhorse, because if we were to take away sawhorse B, then the ladder would rotate around the top of sawhorse A. And if we were to take away sawhorse A, then the ladder would want to spin around the top of sawhorse B. So just arbitrarily, I'll choose the top of sawhorse A as the radius of rotation. Right? And we will define the weight force as causing a torque in this direction. So we will call that tau W. Now that is an clockwise rotation. That's with the hands of the clock. So we will say tau W is negative. And then force of sawhorse B is exerting a force that wants to cause the ladder to spin in the opposite direction. So we will call that tau B. Because that is anti-clockwise, which is against the hands of the clock, and that rotation is just by convention positive. So let's write a net torque formula. Tau net is equal to tau b, which we defined as positive, minus tau w, which we defined as negative. Okay. Because the ladder isn't rotating, we can say that tau net is equal to 0 newton meters, is equal to tau b minus tau w. We can add tau w to both sides. So tau w is equal to tau b, which again should be pretty intuitive. The torque caused by the ladder's weight is balanced out by the torque of the supporting sawhorse. Now we can plug in, we can say that tau w is equal to force w times rw is equal to tau b, which is equal to force b times rb. And force w is the weight, so that's mass times gravity times rw is equal to force b, which is one of the things we're trying to find, times rb. Now let's start plugging in some numbers. The mass of the ladder is 5.8 kilograms. This information was given in the problem. We assume this ladder and sawhorse setup is happening on Earth, so gravity is 9.81 meters per second squared. And RW, that's going to be the distance from the radius of rotation, or the axis of rotation, to the center of mass, which that information is not explicitly given to us, but we can sort of work it out. The center of mass is halfway along the length of the ladder, so that means it is 0.90 meters from one end of the ladder. And sawhorse A is 0.60 meters from the end of the ladder. So the distance from here to here should be 0.30 meters. I paused the video if you sort of need to think about that for a minute and convince yourself that RW is 0.30 meters. All right, next up we have force B, which is what we don't know. We're trying to solve for that. Multiplied by RB. RB is going to be the distance from the axis of rotation to the top of sawhorse B. And this is another distance that is not explicitly given to us. So we're going to have to kind of work it out. We know that the total length of the ladder is 1.80 meters. And we're interested in this distance from here to here. So we're going to take out that 0.60 meters and that 0.15 meters, and what we're left with is this distance from the top of sawhorse A to the top of sawhorse B. So RB is equal to 1.80 meters minus 0.60 meters plus 0.15 meters. So RB is equal to 1.80 meters minus 0.75 meters, or 1.05 meters. Okay, so that was a little bit of a chore, but that's the information we were looking for. Now we've got everything we need to solve for FB. On the left-hand side, we have 5.8 times 9.81 times 0.30. And if we do all that in the calculator and round it down to two significant figures, we're going to get 17 Newton meters. On the right-hand side, we have FB times 1.05 meters. Now divide both sides by 1.05, and again, round your answer down to two significant figures, and you're going to get 16 newtons for FB. So there's the first part of our solution. Now we come back over here to the equation that we set up a minute ago. Mass times gravity is equal to FA plus FB. Now that we know FB, we can solve for FA. The ladder's mass is 5.8 kilograms times gravity, 9.81 meters per second squared, equals FA plus FB, which is 16 newtons. 5.8 times 9.1 is 57 newtons if we round it to two significant figures. And then if we subtract 16 newtons from both sides, we find that FB is equal to 41 newtons. Excuse me, FA is equal to 41 newtons. So the sawhorses exert vertical forces of 16 newtons and 41 newtons respectively, which when added together gives us 57 newtons, which is the weight of the ladder. And that's exactly what we would expect. So that's the end of lesson 5.3, equilibrium. If you have any questions, please be sure to let me know. I'm going to post a short assignment on Google Classroom, no more than 4 to 5 questions, just to check your understanding of the material. I will be offering feedback. And again, as I said, if you do have any questions, please don't hesitate to email me or contact me through Google Classroom, and I'll get back to you as quickly as I possibly can. Tomorrow we will be going over lesson 5.4, which is about centripetal force and acceleration. After that, we will move into our next chapter, and we'll talk more about that when the time comes. I hope you're all having a good day. Please take care, stay safe, keep washing your hands. I'll talk to you tomorrow.